Good afternoon, everyone. I'm Cheng-En from the University of Tennessee. Wildfires have been known as one of the most destructive natural disasters worldwide. Wildfires can worsen regional air quality by emitting large amounts of hazardous gases and particulate matter. These toxics cause adverse health effects such as lung cancer and asthma. Therefore, the group formed by the University of Tennessee, U.S. Forest Service, and Emory University conducted this study to evaluate wildfire impacts on air quality from the present climate to the future climate. In the past 3 decades, the contiguous U.S. has experienced a decreasing trend of fire counts, which is the blue line in this figure. The red line in this figure is the annual burned area, and the green line is the fire suppression cost. We can see millions of acres were burned and billions of dollars were spent each year. Statistics also show increasing trends of burned area and the suppression cost. Now we further look into the western U.S., where it has been struck by many catastrophic wildfires in recent years. On the left-hand side shows the fire counts, and the burned area is shown on the right-hand side. The columns are the actual numbers, and the black lines are the ratios to the contiguous U.S. numbers. If we draw a dashed line at 50%, we can see the fire counts in the western U.S. are mostly lower than the dashed line, while most of the burned area in the contiguous U.S. was attributed to the western U.S. wildfires. According to the 2013 IPCC report, the climate is projected to be warmer by the end of 2100 compared to that during 1986 to 2005, which can be seen in the upper panel, with warmer temperatures shown in red and cooler temperatures in blue. In terms of precipitation, the U.S. will become wetter except for the western part under the representative concentration pathway 8.5 scenario, which is shown in the bottom right panel. Warmer temperatures and reduced precipitation may enhance wildfire activities in the western U.S. and thus increase the health risks due to air pollutants emitted from wildfires, such as ozone and the fine particulate matter PM2.5. Previous studies examined the ozone and the PM2.5 concentration changes in the U.S. between 2050 and 2005. They found substantial reductions of ozone over the southwest U.S. and the eastern U.S., whereas PM2.5 concentration became smaller across the contiguous U.S., mainly because of the emission reductions. So, with the reduced ozone and the PM2.5 concentrations projected in the future, will wildfires become a more important contributor to these two pollutants in the western U.S., giving a warmer and a drier climate? To estimate the wildfire contributions to future ozone and the PM2.5 concentrations in the western U.S., we employed multiple global and regional climate and chemical transport models to simulate the pollutant concentration changes. The study domain is shown on the top right and indicated by the red rectangle. Our simulations focused on wildfire months from April to November, covering the historical period from 2003 to 2010, and the future years from 2050 to 2059 under the RCP 8.5 scenario. The global model output served as the lateral conditions for regional models that have a horizontal resolution of 12 kilometers by 12 kilometers. The historical emissions were obtained from the US EPA. We adjusted the fire emissions using the FIN dataset. For future emissions, we adopted the RCP 8.5 scenario emissions from EASA. which were projected based on the socio-economic activities. Another future wildfire emission dataset was generated from an empirical fire model, which is based on the extreme value theory. The fire emissions depend on the climate conditions, including precipitation, temperature, wind, and relative humidity. And only locations with large fires that occurred during 2001 to 2010 were projected for future years at the same locations. The outputs from this empirical fire model replaced the wildfire emission sector in EASA, while no modifications were made to the other sectors in EASA. To estimate the impact of wildfires on ozone and PM2.5 concentrations, and how wildfire contributions change from the historical period to the future years, we control the wildfire emissions with the same meteorological inputs and the lateral boundary pollutant concentrations. On the left-hand side illustrates the two historical experiments, of which no wildfire emissions as experiment 1, and with wildfire emissions as experiment 2. Similarly, the chart on the right-hand side gives the setup of 3 future experiments, including no wildfire emissions as experiment 3, with EASA wildfire emissions as experiment 4, and the experiment 5 utilized wildfire emissions from the empirical fire model. And in this presentation, only ozone and the PM2.5 will be discussed. Before we estimated the wildfire contributions on ozone and PM2.5, we evaluated the CMAS model performance by comparing hourly ozone concentrations and daily averaged PM2.5 concentrations to the observations from AQS and the improved database during the historical period. We applied the 40 ppb cutoff value for ozone evaluation according to the 2007 US EPA guidance. We used the mean fraction error and the mean fraction bias as the metrics to evaluate the model performance. Based on the table shown here, we clearly see that CMAS simulated both ozone and the PM2.5 well, except the mean fraction error for PM2.5 is a bit higher than the model performance goal, but it still meets the model performance criteria. The wildfire impacts on hourly ozone and the daily PM2.5 concentrations over the western US will be presented in terms of monthly mean domain averages and the maximum change at the grid cell level each month. The figure on the left shows hourly ozone, and on the right shows daily PM2.5. The upper panels are domain averages with the blue line for experiment 1, which is no wildfire emissions, and the red line for experiment 2, which is with wildfire emissions. The lower panels are grid cell level maximum changes. The values can be as high as 175 ppb for ozone and almost 1300 microgram per cubic meter for PM2.5. Note that the summertime is labeled by the light gray columns in each panel. From this figure, we see historical wildfires have small influences on domain averages over the western US. However, we see large wildfire impacts on maximum changes at grid cell level for ozone during summer and for PM2.5 during autumn. To estimate the contribution of wildfires, we calculated the ratios of the difference between with and without wildfires to the values of no wildfire emissions, which can be expressed by this equation. For the two delta Dmax values shown here, wildfire contributions are 11 times for ozone and 157 times for PM2.5 during the historical period. For future years using EASA wildfire emissions, like the historical period, The domain averaged changes are also small, while delta Dmax values are significant, with 102 ppb for hourly ozone and 259 microgram per cubic meter for daily PM2.5. Compared to the historical period, these numbers are smaller, but when we calculate the contribution ratios, we find the wildfires become more important with the contribution up to 214 times for PM2.5. The small wildfire impacts on future ozone concentration changes may be due to warmer climate. Here I want to mention again that the future PM2.5 concentrations are estimated lower than the historical period over the US, as the previous slide has shown. Also, the future emissions were derived based on the US EPA 2005 profiles. Therefore, a fair comparison between the future years and the historical 2005 results should be investigated. Similarly, the experiment using the empirical fire model emissions has very small domain average changes for both ozone and PM2.5 due to wildfires. Much smaller delta Dmax values were also simulated, with the largest contribution ratio of 32 times for PM2.5. The reason for smaller wildfire contributions than EASA is caused by how the wildfire emissions were derived by the empirical fire model, which considers only large wildfires during the historical period and depends only on climate conditions. To further illustrate how the two future wildfire emissions result in different wildfire impact projections, we select three locations at California, Colorado, and Arizona as shown on this map for PM2.5 concentrations during June 2051. The black lines represent the experiment without wildfire emissions, red lines for EASA wildfire emissions, and blue lines for the empirical fire model emissions. On the bottom left, we see the red line, which is with the EASA wildfire emissions, has two major wildfire events in California leading to high PM2.5 levels. On the contrary, there is no wildfire contribution according to the blue line, which is the empirical fire model case. This is because there were no large wildfires at this location during June 2001, and therefore no wildfire emissions were projected at this location. Compared to California, the results for Colorado and Arizona are quite different. The empirical fire model demonstrates high PM2.5 concentrations due to wildfires, whereas EASA has small or no wildfire contributions. In summary, our work shows future wildfires have small impacts on domain averaged hourly ozone and daily PM2.5 concentrations. However, the wildfire contributions to the total PM2.5 become more significant in the future than the historical period. In addition, by checking the whole western US domain as well as three city-level results, we demonstrate that future ozone and PM2.5 changes due to wildfires can differ substantially according to the emission projection methods. First, the wildfire emissions were projected based on 2005 profiles for EASA emissions. And second, the empirical fire model only considered the large wildfire events and only depended on climate conditions. This may imply that small wildfires could have an important role in future PM2.5 concentrations. Lastly, we need more model simulations and analysis with high spatial and temporal resolution so that essential information can be provided for future wildfire and air quality management. Thank you for your attention, and we are happy to take your questions.